Stars are disappearing. Not dying, not exploding in the supernovae that seed galaxies with heavy elements and briefly outshine everything around them. Not fading slowly over billions of years as their fuel runs out. Disappearing. Vanishing from telescope images between one observation and the next, leaving behind nothing. No remnant, no explosion signature, no expanding shell of gas, no neutron star, no black hole we can detect. Here, then not here. Astronomers call them vanishing stars. The formal term is disappearing stars, or in some papers, more cautiously, unresolved transients with no detected counterpart. The caution in the language is deliberate, because the honest description, a star that was there and then wasn't, implies something that the standard models of stellar physics do not have a clean explanation for. Stars do not simply vanish, except that some of them do. And the more carefully we look at the edges of the observable universe, at the oldest light, the most distant galaxies, the regions of space-time closest to the beginning of everything, the more of them we find. Something is removing stars from the universe. We do not know what. The first systematic evidence came from a project called VASCO, Vanishing and Appearing Sources During a Century of Observations. A team of researchers led by Beatrice Villarroel at the Nordic Institute for Theoretical Physics began comparing historical sky surveys from the mid-20th century with modern observations. The premise was straightforward. Take images of the same patches of sky separated by decades and look for objects that appear in one and not the other. They expected to find mostly instrumentation artifacts. Old photographic plates are imperfect. Emulsion defects, processing errors, cosmic ray strikes. The list of things that can produce a spurious bright spot on a historical plate is long. They expected noise. What they found, after filtering for known artifacts, was a residual population of objects that appeared in historical surveys and have no counterpart in modern deep imaging. Objects that were bright enough to be detected by mid-20th century instruments, which means they were not marginal detections, not objects at the edge of sensitivity, and are now simply absent. Not faded, not dimmed, absent. One candidate in particular drew attention. A point source appearing in a 1950 photographic survey, bright enough to be a star in the Milky Way or a compact object in a nearby galaxy, with no counterpart in any modern image down to detection limits far deeper than the original observation. Whatever it was there in 1950. By the time modern instruments looked at the same coordinates, it was gone. The team published their findings carefully. They did not claim aliens. They did not claim a new physics. They presented the data and listed the possible explanations ranked by plausibility. None of the explanations were fully satisfying. The most conservative explanation is failed supernovae. When a very massive star reaches the end of its life, the standard outcome is a supernova, a catastrophic explosion that tears the star apart and leaves a neutron star or black hole at the center. But simulations of stellar collapse have long suggested that for some mass ranges, the collapse does not produce an explosion. The core implodes. The shockwave that would normally produce the supernova stalls and fails. The outer layers of the star, without the energy of a successful explosion to lift them away, fall back inward. The entire star collapses directly into a black hole. No explosion, no bright display, no expanding remnant, just a star that was there, and then a black hole that is too small and too dark to detect at the distances involved. This is called a failed supernova or a direct collapse event. It has a theoretical basis. The simulations produce it under specific conditions, and in 2009, astronomers monitoring a massive star in the galaxy N6946BH1 watched it brighten briefly and then fade. Not explode, but fade below detectable limits. The star, designated N6946BH1, was estimated to be about 25 times the mass of our Sun. It is now gone. One candidate, watched in real time, apparently vanishing. Failed supernovae are real. They almost certainly account for some fraction of the stars that disappear from survey images. But they do not account for all of them, because here is where the distribution of vanishing stars becomes strange. If failed supernovae were the primary explanation, you would expect vanishing stars to be distributed roughly uniformly, appearing wherever massive stars exist in proportion to the stellar populations of different galaxy types and epochs. They are not uniformly distributed. The signal of anomalously vanishing sources, objects present in historical surveys and absent in modern imaging, is stronger at high redshift, farther away, earlier in cosmic time. In the regions of the observable universe closest to the edge of what we can see, where the light reaching us left its source billions of years ago, the rate of unexplained disappearances appears elevated compared to what stellar physics predicts. Something at the edge of the observable universe is removing stars, or something that looks like stars, at a rate that exceeds what failed supernovae can account for. The edge of the observable universe is not a special place physically. It is a special place observationally, the limit of how far back in time we can see, defined by the age of the universe and the speed of light. Galaxies at the edge are not stranger or more exotic than nearby ones. They are simply older. The light reaching us is ancient, and in that ancient light, more things are disappearing than should be. This is where the explanations stop being conservative. One hypothesis involves a class of objects called Thorne-Zytkow objects, a theoretical stellar type proposed by astronomers Kip Thorne and Anna Zytkow in 1975. A Thorne-Zytkow object forms when a neutron star merges with a giant or supergiant companion star. Not a collision in the ordinary sense, but a slow in-spiral, the neutron star sinking into the envelope of the larger star and eventually reaching its core. The result is a star with a neutron star at its center instead of nuclear fusion, powered by accretion rather than fusion, with surface chemistry that differs from any normal stellar type.
Thorne-Zytkow objects were theoretical for decades. The first candidate was identified in 2014. They are expected to be rare and short-lived on stellar timescales. Eventually, the neutron star consumes or disrupts the host star, and the combined object either collapses or disperses. A Thorne-Zytkow object that reached the end of its existence might disappear without the characteristic signature of a normal stellar death. A star that was there, cataloged, measured, assigned coordinates, and then simply not there as the internal dynamics reached their conclusion. But Thorne-Zytkow objects are expected to be extremely rare. They cannot explain a statistically significant excess of disappearances across multiple surveys and epochs. Then there are the explanations that require new physics. Some researchers have proposed that a fraction of the vanishing sources could be stars undergoing a phase transition, a hypothetical process in which normal matter, under certain extreme conditions, converts to a more stable form called strange quark matter. In this scenario, a star does not explode or collapse in any conventional sense. Its nuclear matter undergoes a sudden, rapid conversion to a different state of matter, releasing energy in a brief burst and leaving behind a strange quark star, an object so compact and so dark that it is effectively undetectable at cosmological distances. The conversion would be fast, the optical signature would be brief. What you would observe is a brightening followed by a vanishing, the star disappearing into something too compact to see. Strange quark matter is hypothetical. Its existence is suggested by certain extensions of quantum chromodynamics, the theory of the strong nuclear force, but has never been confirmed experimentally. A strange quark star has never been conclusively identified. The hypothesis is mathematically coherent and physically unmotivated by direct evidence. But it is not ruled out, and it would explain a star disappearing. Here is where the story makes its sharpest turn. In 2019, A paper published in the monthly notices of the Royal Astronomical Society by researchers including Villarreal's team examined a specific subset of the vanishing source candidates, those with the most robust historical detections and the deepest modern non-detections. They analyzed the spatial distribution of these candidates and found something that the failed supernova and stellar physics explanations do not predict. Some of the candidates appeared not in isolation, but in clusters. Multiple vanishing sources in proximity to each other in regions of sky where the density of such events exceeded what random distribution would produce. Clusters of vanishing stars. The paper was careful. The authors noted that clustering could result from systematic effects in the historical photographic data, emulsion in homogeneities that produce spurious sources in certain regions of a plate. They could not rule out instrumental artifacts as the explanation for the clustering. But they could not confirm it either. The clustering signal survived their artifact tests. Whatever is removing stars from the sky, failed supernovae, phase transitions, something unnamed, it may not be doing so uniformly. It may be concentrated in specific regions, operating preferentially in certain environments. We do not know what those environments have in common. There is a parallel line of investigation that adds another layer to this story.
The Laser Interferometer Gravitational Wave Observatory, LIGO, and its partner detectors have been detecting gravitational waves since 2015. These are ripples in space-time produced by the most violent events in the universe, merging black holes, merging neutron stars, potentially other extreme events. Among the confirmed and candidate detections is a class of events whose electromagnetic counterpart, the light, X-rays, gamma rays that should accompany certain violent events, is absent or anomalously faint, gravitational wave sources with no visible optical signal, something producing ripples in space-time without producing the light that the standard models predict should accompany the event. These are not the same as vanishing stars. They are a different observational phenomenon, but they point in a similar direction. Events occurring in the universe that do not produce the electromagnetic signatures that our models say they should. Things happening that we can detect only partially, or only indirectly, or only in the gaps between what we expected and what we found. The universe is doing things that leave incomplete signatures, and the incomplete signatures are accumulating. Let's be precise about what is established and what is not. Vanishing stars are real. The VASCO survey and follow-up work have identified a population of historical point sources with no modern counterpart that cannot be fully explained by instrumental artifacts. The number of robust candidates is not enormous. It is in the dozens to low hundreds, but it is statistically significant relative to what artifact rates predict. The explanation is unknown. Failed supernovae are the most physically motivated candidate and almost certainly account for some fraction of the population. But failed supernovae alone do not appear to explain all of the candidates, particularly those at high redshift and those showing spatial clustering. Beyond failed supernovae, every proposed explanation is either unconfirmed or speculative. Phase transitions to strange quark matter, exotic stellar mergers, direct collapse events of types not yet simulated, processes not yet proposed. This is not a solved problem wearing the costume of a mystery. It is an actual open question in observational astronomy with data that does not fit the existing framework and no consensus explanation for the excess. The universe is 13.8 billion years old. The observable portion of it extends approximately 46 billion light-years in every direction, a sphere of space-time containing 2 trillion galaxies, each containing hundreds of billions of stars. We have been conducting systematic photographic surveys of the sky for roughly 100 years, deep digital imaging for approximately 30. The fraction of the sky we have surveyed with sufficient depth and temporal coverage to detect vanishing stars is a small percentage of the total observable universe. We found dozens of robust candidates in that small fraction. Extrapolate to the full observable universe across the full survey depth that a future telescope capable of monitoring every galaxy to sufficient sensitivity would provide, and the number of unaccounted for stellar disappearances is not dozens, it is potentially millions. Something is removing stars from the universe at a rate that failed supernovae cannot fully account for. The removal is preferentially concentrated in the early universe, in the oldest light, the most distant galaxies, the epoch closest to the beginning. And the mechanism, whatever is doing this, leaves no clear signature in the light we collect, no obvious remnant we can identify, no process that the standard models of stellar evolution cleanly describe. We are watching the universe from inside it, with instruments that have existed for a century, looking at light that has been traveling for billions of years. And in that ancient light, things are missing. Not catastrophically, not in numbers that dominate the stellar census or reshape our understanding of cosmic history, but measurably, statistically, in patterns that cannot be fully explained by what we know. Every time astronomy has found something disappearing without explanation, the eventual answer was something new. Pulsars disappeared and reappeared on timescales that seemed impossible for any known stellar object. They turned out to be rotating neutron stars, a class of object not previously confirmed. Gamma-ray bursts appeared and vanished in seconds, seemingly random, seemingly sourceless. They turned out to be the deaths of the most massive stars and the mergers of the most extreme objects in the universe. Fast radio bursts appeared from cosmological distances with no known mechanism. They turned out to be probably magnetars, and their full diversity is still being catalogued. In each case, the disappearance was the signal. The thing that was there and then wasn't was telling us something. The absence was the discovery. What the vanishing stars are telling us, we do not yet know. But the signal is there, in historical photographic plates and modern digital surveys, in the careful comparison of then and now, in the statistical excess that remains after every artifact is accounted for. Something at the edge of the observable universe is consuming stars, or transforming them, or removing them by a process that leaves no trace we currently know how to read. The stars were there, and then they were not. And somewhere in the distance between those two facts, in the gap between presence and absence, between the old image and the new, between what the universe was and what it is now, something happened. We just don't know what yet.